I know that we need it for this upcoming homework set, but we definitely will for the one after it. So I want to talk again about how we set up for an inclined plane. So let's say we've got an inclined plane there. It's at some angle theta down here. And we've got a box or whatever sitting here. We know that one thing we want to do to make this easier on us is to rotate our x and y axes. So instead of being vertical and horizontal, we're going to rotate them to match the incline, because most of our forces are either parallel or perpendicular to this incline. So that would mean y is like that, x is like that. But that introduces a problem because of gravity. Gravity is straight down, mg. That's how much force is acting because of gravity on something on this incline. I want to relate that and say, okay, that means that I'm going to have some component of gravity that goes down, and I'm going to have some component of gravity that goes straight into my ramp and is combated by the normal force. And I want to go back and say, okay, how do I know which one's which? And I'm going to use some geometry for that. I'm going to call this angle phi, and then, because in physics, theta is always our first angle, phi is always our second. It's just what they do. And this, because it's straight down, is going to be right angle. Well, triangles, as we know, the interior angles add up to 180. So if this would be whatever 180 minus the sum of those two. So it would be 180 minus the 90 degrees for a right angle, minus whatever theta is, right? So that angle is 90 minus theta. That could be useful, but there's an even better way to do it. Now I'm going to draw another line here, see what best I can do it, perpendicular to my ramp. And then I'm going to move it so it's right there. I'll extend that. Okay, so now let's look at this. This is a right angle right in there. I want to look at my big triangle now. Well, if I look at my big triangle, I just made this perpendicular, right? So I've got one side that's theta, one side that's 90. That means this must be the same. This must also be phi.
Wait, what's that line?
This one? Yeah. Just a perpendicular line. So that'll be the normal force. It's my y-axis in this. X-axis is the slope itself. And I'm just extending this out so I can get a measurement that makes sense. So this one, because we have theta on this corner, we have a right angle up here, means this one is a congruent angle to the one I just looked at. Same sort of triangle. It's a similar triangle. This triangle is similar to this triangle. And so that angle, those two angles are the same. Well, what about that angle right there?
That's theta.
Right, because it would be 180 for the whole triangle, minus our phi, minus the 90 from that right angle, or in other words, 90 minus phi. Well, I already know what phi is. It's 90 minus theta. So if I take 90 minus that, I get 90 minus 90 plus theta. That means that angle right up there is also theta, the angle of the incline. Okay, so all of that was just to prove that I can use this in the rest of it. Does that part kind of make sense? And okay, so that's theta. I'm going to erase some of this other stuff so that, because I don't need it for the next thing. And from now on, we'll just, believe, that's theta. Okay. So now what I want to do is, I really can only work in X and Y to make this make sense. So I have to get which parts of MG are along X and which parts are along Y. Right? I need to get those components. So what I'm going to do to make this make sense, I'm going to label that. I have got a right angle here because this is a horizontal thing. The gravity is straight down, so that's a right angle, and I know that angle theta because that's how I set up my ramp. So that's not what I want. Sorry. I actually want it along X and Y. I don't want to work with this. I want to work with X. Let's make sure that those are parallel. Scratch it. So it's confusing because you got to work on it, and because I said it wrong there in the first part. Here's the triangle I want. My apologies. I want to find the part that's along X, which is now parallel to this, and the part that's along Y, which is parallel to that axis. I know the hypotenuse. And I know that angle because that's the angle that my ramp is inclined at. So that's the opposite side of my triangle. Which trig function relates the hypotenuse to the opposite side? Sine. Sine is opposite over hypotenuse. That means that, so if I took the sine of theta, that would be equal to the opposite, which is what I want to find. The force in the X over the hypotenuse mg, so that the force going down here is actually mg sine of theta. That's what that component is. So this is the amount of force going down the ramp related to the weight. Here I have the adjacent side. Well, adjacent and hypotenuse are related by cosine. So that means this side would have a value of mg cosine theta. So that gives me the amount of force actually going perpendicularly into my ramp. These are the two that are going to be important to us when we're trying to solve any of these equations, because I would have, if this were just sitting here, I'd have friction going on the X, I'd have a normal force combating that, and that's what allowed me to write the equations at the beginning of the last lap.